Hello friends, today the topic of our learning session is Nand and Nor as universal gates. Before starting with today's topic, I would like to have a quick recap of what we already know about logic gates. First is NOT gate. Here the output of the gate would be totally in the opposite manner, or I can say the output would be totally complement of what has been applied at input. If suppose I am applying logic low in my input, the output would be logic high and vice versa. The next gate is AND gate. Here from the truth table it can be easily known that the output of AND gate would be high only when my both the inputs are at logic high. The complement of AND is NAND gate, and thereby it can also be known as NOT AND gate. The truth table of NAND gate is totally the complement of what is of AND gate. Next is OR gate. Here from the truth table it can be easily identified that my output would be logic high if either of the two inputs or both the inputs are at logic high. The complement of OR gate is NOR gate, that is not OR gate, and the output is totally in the inverse form of what is of OR gate. Next gate is XOR gate. XOR is also termed as inequality detector, as the term inequality suggests. Whenever my both the inputs would be unequal, that is, my either of the input would be at logic low and the other would be at logic high, my output of the gate would be high, else my output would be 0. And the last gate is XNOR gate, which is termed as equality detector, as the term equality stands. Whenever my both the inputs would be same, that is either logic high or logic low, my output would be high, else my output would be low. Now we would be deriving all the logic gates using universal gate. First of all, we would be discussing about NAND gate, NAND as NOT gate. As we know that NOT is a single input gate, we need to convert the two input gates into the single input gate. That is, we can short both the inputs and convert the two input NAND gate into a single input NOT gate. Here we are shorting both the inputs. We will be implementing the same using multisim and check the output. Here we would be first of all taking one NAND gate, then we would be taking the single pole double throw switch, then we will be taking the power sources that are VCC and ground. And for the indication of my output, I will be taking indicator probe. I will be rotating this switch for my simplicity. I will be connecting the terminal of the switch with one of the input of the NAND gate and will be shorting the other. I will be connecting one of the terminal of the switch with ground and the other with VCC, and we are connecting the output of the gate with indicating probe and would be running the circuit. Here my switch is initially connected with the ground and thereby my output is logic high. Whenever I would toggle my switch with my input as VCC, my output would be 0, which is the functionality of NOT gate. Here we have implemented NOT gate using NAND gate. Now My next is NAND as AND gate. The Boolean expression corresponding to NAND gate is x dot y whole complement and that of AND gate is x dot y. Now looking at the output in the truth table, we can easily identify that the output for AND gate is completely toggled to that of the NAND gate. That means on application of one single module of NOT gate, I can convert my NAND gate into AND gate. We would be looking and executing the same connections in multisim. This is the connection corresponding to AND gate. Here the output of NAND gate has been connected with NOT gate and the probe will indicate me the final output. I am running the circuit. Initially my both the inputs are at ground, that is logic low, and my output is also 0. Whenever I will connect my both the switch with VCC, that is logic high, my output would be at logic high state, which is the functionality of AND gate. Now my next portion is NAND as OR gate. We know the Boolean equation for NAND gate is x dot y whole complement, which is equal to x complement plus y complement as per De Morgan's law. But we need the equation in the form of x plus y, which is the Boolean expression corresponding to OR gate. So what changes shall we do in order to obtain x plus y instead of x complement plus y complement? The answer is simple. Application of NOT gate before NAND gate would result me in x complement and y complement, and I can easily convert my NAND gate into OR gate. This is the connection for NAND gate as OR gate. I am running the circuit and here my both the switch are connected to ground, that is I am applying logically low on my both the inputs and thereby my probe indication is logically 0, that is logically low 0. Whenever I would connect either of the switch with VCC, that is logically high, my probe would get on. This is the same functionality as OR gate. Now the next topic is NAND as XOR gate. We know that XOR gate is called the inequality detector. The equation for XOR gate is A XOR B, which is equal to AB complement plus A complement B. On applying the double complement to the input, we get the input back as the final result. On application of the same phenomenon, we are going to apply twice the complement onto the equation of A XOR B. Now, on application of the De Morgan's law, we are going to get the equation that has been shown here, and now we will be running the same equation in multisim. This is the circuit that resembles to the equation that we have obtained. Here initially both the inputs are connected to the ground, that is logically low. Thereby the probe indication is 0. Whenever I would connect one of the switch to VCC, that is logically high, my probe would get logically high. And if I connect both the input at VCC, my probe would again get off, which is the concept of XOR, which is inequality detector. The next is NAND as XNOR gate, and XNOR gate is also known as equality detector. The Boolean expression for the same is A complement B complement plus A B. The same fundamental of replication of the double complement to the input, we get the input back as the result. On application of the De Morgan's law, we are going to get the NAND gate as XNOR gate. Now we would be looking in multisim the output of the XNOR gate. This is the circuit connection for NAND as XNOR gate. Here, initially, both the inputs are connected to ground, and as per the definition of XNOR gate, I would be getting logically high whenever my both the inputs would be same, since XNOR is an inequality detector. Whenever I would move one of the input to logically high and the other would be at logically low, my output would be 0. And again, whenever I would be applying the same input, my output would be logically high, which is the functionality of XNOR gate. Till now, we have looked for the implementation of the logical gates using NAND gate. Now we will be looking forward for the implementation of the same gates using the other universal gate, which is NOR gate. First is NOR as NOT gate. For the conversion of NOR gate as NOT gate, we would be implementing the same concept that we have used in converting NAND as NOT gate. We would be shorting both the input terminals, since NOT is a single input gate, and thereby we would be getting, instead of x plus y the whole complement, we would be shorting both the terminals and would be getting the Boolean expression corresponding to the NOT gate. We would be implementing the same circuit in multisim. This is the circuit that I have already drawn in multisim corresponding to the equation that we have obtained for NOR as NOT gate. I would be running the circuit. Initially, my switch is connected to the ground, and thereby the input to this NOR gate would be logically low, and as a complement I would be getting logically high as my output. Whenever I will toggle my switch to VCC, that is high, I would be getting logically low as my output. This is the concept of NOT gate using NOR gate. Next is NOR as OR gate. As we have discussed earlier, NOR can also be represented as NOT OR. The Boolean expression corresponding to NOR gate is x plus y whole complement, and that for OR gate is x plus y. Looking at the truth table, we can easily find out that the output for NOR is exactly the complement to that of OR, and thereby on application of one of the step, I would be converting my NOR output into OR, and that step would be implying NOT gate in the output of NOR gate. This is the circuit corresponding to the connection for OR gate. Here the output of NOR gate has been connected with NOT gate, and thereby the indication probe. I will be running this circuit, and initially my both the inputs are connected with ground and the output is logically low. Whenever I would toggle one of the switch connection with VCC, my output would be logically high. This is the working of NOR as OR gate. Our next portion is NOR as AND gate. The equation for NOR gate is x plus y whole complement, and on application of De Morgan's law, we would be getting x complement dot y complement. Now here we can easily analyze that in order to convert x complement into y complement into x dot y, which is the equation corresponding to AND gate, I need to toggle my input. Thereby, I would be applying NOT gate before my NOR gate so that my input x gets converted to x complement and y gets converted into y complement. Now we will be applying the same connection and look for the output in multisim. This is the connection corresponding to AND gate. Here I have applied the shorted NOR gate, which works as NOT gate, and the output of both the NOT gates would be applied to NOR gate to implement AND gate. I am running the circuit. Initially both the inputs are at logical low, that's why the output would be low. Whenever I would toggle one of the switch, still my output would be logical low, since my AND gate would only reflect logical high when my both the inputs would be at logical high. That is, now I am applying both the inputs with VCC and thereby my output is reflected as logical high state. Next is NOR as XOR gate. The equation corresponding to XOR gate is A XOR B, which is nothing but A B complement plus A complement B, which we have already discussed as inequality detector. On application of double complement rule and then followed by De Morgan's law, I will be getting the simplified solution, which is still not in the form of NOR gate. So I will be again apply De Morgan's law twice to the equation, and thereby I will be getting some simplified equation. Here the first term is in the form of NOR gate. Let's call it as X. The second term is in the form of NOR gate. Let's call it as Y. And the combination of both the terms would be applied to the another NOR gate. Let's implement the same Boolean expression in multisim. This is the circuit corresponding to XOR gate that I would run based on the Boolean expression that we have obtained. I will be running the circuit. Initially, my both the switch are connected with ground, that's why I am getting output as logically low state. Since XOR is the inequality detector, whenever I would change my one of the input state to logically high state, my output would be logically high, since XOR is inequality detector. And the last is NOR as XNOR gate. The Boolean expression corresponding to XNOR gate is A complement B complement plus AB, which is the equation corresponding to equality detector. On application of the double complement rule, now I will be applying De Morgan's law thrice to get the simplified Boolean expression, but the still expression is not in the form of NOR gate. The two terms A plus B whole complement and A complement plus B complement the whole complement are in the term of NOR gate, but the entire expression is still not in the form of NOR gate. Since we have to obtain the expression in the form of NOR gate, that is OR plus NOT, we will be again applying the double complement rule. The two terms are in the form of NOR gate. Now we will be applying the Boolean expression in the circuit form and look for the output in multisim. This is the circuit corresponding to the Boolean expression that we have obtained. I'm running this circuit and initially my both the inputs are connected with ground, that is logical low, and my output would be 1 since XNOR is the equality detector. Whenever I would toggle one of the switch, my output would get low. Again, whenever I am applying logical high state on both the inputs, my output would be logically high, which is the concept of XNOR gate. Thanks for your kind attention.